Single sideband transmission, the requirement for the correct beat frequency oscillator phasing is not critical if one of the two sideband is transmitted to save the bandwidth requirements. Okay, so the sidebands, since they are the mirror images of each other, so they carry the same information, and one will do. So, for example, like before, if you are going to transmit your uh, either the upper sideband or the lower sideband. Okay, so the situation is like this. At, let's say, at omega c, this is your carrier frequency, omega c, and you have to select either the upper sideband or the lower sideband because it is the mirror image. So this is the upper sideband, then you have the lower sideband. Okay, since the two are the same, you can choose any one of them to save the bandwidth. So the easiest method for transmission of one of the sidebands, assuming that the carrier is suppressed, is to use a bandpass filter. Okay, so for example, this frequency is your omega c, again omega c plus, let's say, omega a. Okay, my audio bandwidth. Okay, we can bandpass filter this out. We can bandpass filter it. So the bandpass filter, if this was to be centered at DC, then the bandwidth is omega a. That is the bandwidth of the audio signal. So you can select this upper sideband for transmission. Okay. So we will discuss later three methods to eliminate one of the sidebands from a double sideband suppressed carrier signal. So once you have suppressed the carrier, you have saved the power requirement. If you're going to suppress one of the sidebands, you save the bandwidth as well. But the first and the most obvious method, again, is to use a bandpass filter that select the desired sideband. Okay, so you can use a bandpass filter of the same bandwidth. The bandwidth of the bandpass filter is omega A, which is the bandwidth of the audio signal. Now, the resulting signal is known as a single sideband suppressed carrier SSB-SC, or simply SSB, or single sideband. Okay. So let's take the previous example. If you have a single tone of 400 Hertz, so if this were to be a single tone, you have a tone of 400 Hertz over here that is above the carrier frequency. So the single sideband transmitter will put out a single frequency 400 Hertz above the frequency of the suppressed carrier if you have selected the upper sideband. Now, what happened in the super heterodyne receiver is that since this is shifted to the intermediate frequency omega IF, okay, which is usually lower than omega C. So what happens is that your entire spectrum of the signal is shifted at the intermediate frequency. So in that case, omega A is greater than omega IF instead of omega C. So the signal will appear in the receiver 400 Hz away from the intermediate center frequency. So suppose we are still using the beat frequency oscillator and an envelope detector. Because you have to use the envelope detector, we need to employ a BFO to insert the carrier with the correct phase and correct frequency. So if you're using this method of detection, and we have this 400 Hz signal, okay, that is away from the intermediate frequency, the envelope of the signal plus BFO will indeed be an undistorted sine wave. 400 Hz. So far so good, no problem. Okay, because if you have inserted the carrier frequency using a beat frequency oscillator, or you use a voltage control oscillator or pilot, use a pilot from the transmitter, and then you use a VCO to lock the phase, so it's creates zero phase distortion. So if you reinsert the carrier without any phase error, and then you imply or use and the detector, you will have an undistorted sine wave. Okay, even if the signal is translated down to the intermediate frequency of super heterodyne receiver, so it's good. But suppose there's a condition that if the signal has two tones, in this situation, let's say one is at 400 and the other is 600. So actually, what happened at the heterodyne at the super heterodyne receiver IF stage is that they would have been mixing. Okay, they would have been mixing because you recall the FL low was equal to, sorry, the FL low, local oscillator frequency, was FRF, the radio frequency was tuned to radio frequency plus an intermediate frequency. Okay, Now, since you are from the antenna, you are receiving another tone. That's called this FR2. Okay, FR2. And if you're going to mix up these two signals, FR2 is different from FR1. Okay, of course there will be at the IF stage, at the output there will be a difference. So let's call this FR1. So you will have basically FR2 minus FR1. So RF2, sorry, RF2 minus RF1, and then you have this intermediate frequency. Okay, so there's a distortion over here. If you're not going to select the, of course, you're not going to select the higher frequency. So when the BFO carrier is added, the resulting envelope will have two tones, 400, 600, but it will also have a component that is the difference of these two tones, which is distortion. So basically, this term over here is going to create distortion in the envelope detection. Even with the beat frequency oscillator that is inserting the carrier, that is going to insert the carrier at the correct phase, due to the IF stage mixing, there will be a difference of components of two tones, which is going to produce distortion in the envelope. So envelope will not be of that of 600. It will create it will have another component, an AC component of 200 hertz. So this basically the strength of these unwanted signals, which is produced by the IF component beating with each other, their strength is proportional to the product of the two IF signals, right? Basically, you're producing the product with FR2, and then you have another frequency FRF1 where the local oscillator was tuned. So it's proportional to the product of these two frequencies. But in case uh, since the strength of each wanted component on the other hand is proportional to the product of its amplitude times the amplitude of the BFO, beat frequency oscillator, which is inserting the carrier, and if the BFO amplitude is much greater than the IF signal, with the correct, of course, the correct phase and frequency, the amplitude of the reinserted carrier is much higher, then this distortion due to the IF stage, it can be reduced. Okay.